Hello guys, welcome to the live stream of digital communication. Today we are going to understand the science and the engineering behind the transmission of signals, particularly those who are used, which are used in communication. Okay, so let me show you the syllabus. So we are going to study with the map of this syllabus. Here we have information theory, some theorems, then sampling process, sampling theorem, and then waveform coding techniques, then digital modulation techniques, and then data networks. So we are going to use this book. This is by Ali Ibrahim, I think. Let me see. This is 382 Introductions to Digital Communication, Ali Grami. Okay. So 382. We are going to start with information theory. So let's start. To provide a quantitative measure of information, we assume the source is a discrete source. Discrete source means the graph will be in a broken manner, not in a continuous time signal. Okay, this is a reasonable assumption as continuous sources can be turned into discrete sources using analog to digital conversion techniques. A discrete information source has only a finite set of output symbols. Information sources can be classified as having memory or being memoryless. A source with memory is one for which the current output symbols depend on some of the previous output symbols. A memoryless source is one for which the current symbol is independent of all previous output symbols. A discrete memoryless source, DMS. So let me just note it down. DMS is discrete memoryless source, also known as zero memory source. So this is also called as zero memory source. Generates a sequence of independent identical distribution random variables and take that in a discrete set. In other words, DMS produces symbols from the alphabet consisting of k, statistically dependent upon M1, M2, M2. We will understand by the example. Okay, it is intuitively you can see the sum of all the signals. You know, not the signals, the symbols is one. In other words, a DMS produces symbols from the alphabet consisting of statistically independent symbols M1, M2, and till Mk, whose probabilities of occurrence are P1, P2 respectively, and the sum of the probability is 1. It is intuitively obvious that a meaningful measure of information for symbols produced by DMS requires to be monotonically decreasing function. That is, high probability of occurrence conveys relatively little information, as well as continuous function of the probability of the source symbol. Bring out the slide change. The measure of information should also be a function that when an event is almost certain to occur, that is, the event occurs with the probability close to 1. Zero information is almost conveyed, and when an event is almost impossible to occur, it is the probability of the occurrence is approximately 0. An infinite amount of information is conveyed. It should also be a function that gives non-negative information for any event, regardless of its probability. Lastly, the function should reflect the fact. Okay, so there are some conditions. The first one is if the occurrence of the function, okay, is close to 1. The probability. Yes, the probability of the occurrence is close to 1. The function condition. If P is very close to 1, then the information transmitted is 0, 0 info. If P is very close to 0, then infinite info. Okay, infinite information. Second condition was it should also be a function that gives non-negative information. So non-negative info. Okay. And lastly, the function should reflect the fact that the total information received from two statistically independent events is the same as the sum of the information contained. Total information received is equal to sum of the information contained. Assuming the information content of signal mi and denoted by I, the function of the defines the information content must follow the essential. Yes, if it is close to okay, one of the signal is greater than the other signal, then the probability will be opposite. The probability of the first occurrence will be less than the second one. If the first will tends to zero, then the probability tends to one. If the info tends to infinity, the probability tends to zero. It should be non-negative. Okay, and the probability should be 0 to 1, in between 0 and 1, and the addition, the sum of the information is equals to the total info transmitted, and the probability should be 1. So these are the three rules, three conditions. Okay, the only function that satisfies all these requirements is the log function as defined below. So you can see this is, you can also say this is the general term. So I information is equals to log 2 1 upon probability is equals to minus log 2 probability in bits. The base of the log is assumed to be 2 and the information is specifically in bits because the base is 2, so this will be in binary per symbol, bits per symbol. Note that in order to determine the information content using this equation, we can use this relation, okay? So, what it means is, this is a simple thing, simple mathematical equation that if we want to change the base, we can do this, x log 10x divided by log 10 to the base, to find a logarithmic in base, to find the value of x. Okay. As how the okay, using the familiar bit as the information unit of information, it is based on the fact that two possible binary symbols occur. Yes, that is 1 or 0, and the probability is half. If the correct amount of information carried is minus log 2 half, the probability is half, so that's why is equals to 1 bit. That is, 1 bit is the amount of information that can be gained when one of the two possible and equal likely events occurs. Information content of an event in terms of the probability of the event. Okay, this is the log function. There is a simple question. Let's just solve it. So the question is 9.1. A random experiment having a six-sided fair dice die. So determine the information content associated with each outcome. Since the die is fair, the probability will be of each number will be 1 by 6. Okay. Therefore, using the formula log 2 1 upon probability. So 1 upon 1 by 6, log 2, 1 upon 1 by 6, that is log 2, 6, that is equals to approximately 2.585 bits. Or we can also say minus log 1 by 6 bits, where I is equals to 1 to the 6 years. Average information content. The instantaneous flow of information generated by a source may fluctuate widely. Yes, it will. Involved in the symbols that the source selects. Thus, we are more interested in the average information content. Okay, content that a source produces than the information content of a single symbol. The average information content per symbol is called entropy. Getting flashbacks from chemistry. Entropy. So here, entropy means the average information content per symbol. Okay, it's called entropy or equivalent uncertainty. Heisenberg's uncertainty principle. Okay, of the discrete memory, the source X with K symbols is given by the entropy is Hx is equals to entropy of the information IMY, which is the sum of average sum of probability into information I to K. And here we know that the information was log with base 2 1 by probability or minus log 2 1 by just probability. So here is the minus. So we can say this will become minus I to K probability into log 2 probability. Okay. Where this denotes the expectation operator for x equals to 0. The source entropy Hx can be summed as the average amount. A simple interpretation of the synergy source entropy is that on the average we can expect to get h bits of information perceivable in long messages from the information source X, even though we cannot say in advance what symbol sequence will occur. In other words, the source entropy is the measure of the lack of knowledge before the source symbol is revealed. The entropy Hx of a DMS is bounded as follows. DMS was what was that? Discrete memoryless source. So of a DMS, entropy of a DMS should be greater than 0 and less than log 2k, where k is the number of distinct symbols in the DMS. The upper bound of the on the entropy is achieved if and only if probability is 1 upon k. So this is probability for all values of k. In other words, when all the symbols in alphabet set are quite likely to occur. I don't know what this means. Let's just solve the question here. A binary source produces a symbol 1 with probability p and a symbol 0 with probability 1 minus p. Derive and plot the source entropy in terms of p. Using, we will have minus p log 2p minus, because we have to get the sum and this minus comes from the log minus. So this is actually the sum and we're using minus sign because of the log. So minus p log 2p minus 1 minus p log 2 1 minus p with take the derivative of hx with respect to p and then set it to 0 to obtain the maximum value of entropy as shown in figure 9.2. Where is figure 9.2? This is the figure 9.2. So this is the graph. So first, what have we done is we have to derivate this with respect to p. So this will become dh by dx, sorry, dhx by dp. This will become minus 1. This will be 1 upon p. Now this will become, okay, we'll solve in the notebook. The maximum value, as shown, the maximum value is 1 bit. The maximum entropy occurs when p is equals to 0.5. So we will put the value of p is 0.5. When the percentage is maximum or equivalently when the binary is actually true. However, if p is equal to 0 and 1, the binary source symbols are all zeros and ones. When all symbols are zeros and ones, the uncertainty is thus 0. That is hx equals to 0 as the source will source. If the source emits R symbol per second, the average source becomes R, RHX, where R is bits per second because this was bits and this is per second, symbols per second. Bits per symbol, symbol per second. It cuts out to be bits per second. The next question. A memoryless source can generate one of the four symbols A, B, C, and D. The probability is 0.5, 0.25, 0.125, and 0.125. Assuming the source emits at the rate of 8 million symbols per second. So 8 million symbols per second. So one thing was bits per symbol, and the other thing was the answer was bits per second. So this should be symbol per second. So we have got the value of R, small r here, determine the average source information. And we know capital R is equals to small r into hx. Using this, okay, we can directly get the value of hx. So half is 1 by 2. So 1 by 2 log 2 1 by 2 minus 1 by 4 log 2 1 by 4 1 by 8 log, okay, we'll get 1.75. Now using this, the average source entropy information is this as follows. R is equals to, we have the value of small r and 1.75, so we'll get 14 mbps. Very easy question. Extended DMS. What is extended DMS? For a DMS, blocks of symbol rather than individual symbols. Okay. Okay. What we'll do is now the HX, there was single symbols per second. No, it was bits per symbol. So now we will group the symbols, where each block may consist of n successive source symbols may be considered, with k as the number of distinct symbols produced by the source. There are k to the power of n distinct blocks in an extended source. In the case of DMS, the probability of each these blocks of n is equal to the product of probabilities of the n sources. The entropy of the extended is thus equals to n times the entropy of the original. Okay. So entropy of extended symbol, that is x h xn is equals to n hx. Okay, 9.4. We are getting questions so frequently. A DMS can generate one of the three symbols x1, x2, x3, probably 0.5, 0.25, 0.25. Determine the entropy h xn for n is equals to 1 and n equals to 2. So the normal hx would be half log minus half log 2 half minus 1 by 4 log 2 1 by 4 minus same thing 1 by 4 log 2 1 by 4. So it will become minus 1 by 2. So this is minus 1 and this will become half of minus 2. So when we will add this, we will get minus 1. So it will become plus 1 plus 1 by 2. So 1.5 is the answer. 3 by 2. Yes, we got this. Since the source has three distinct symbols, the second order extension of the source has nine distinct symbols. Eh? How? Since the source has three distinct symbols, x1, x2, x3. Okay, now it will group. So x1, x2, x2, x3, x x1, x3. So here we will get 9. And we know uh, the to find the probability of groups, what we'll do is as x1, x1 is half into half, 1 by 4. x2, 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 x3, because x2 and x3 are equal. So x2, x2, x3, x3 here, and x2, x3, x3, x2 will be 1 by 16, and x1, x2, x2, x1, x3, x1, x1, 1 by 8. So using this, we have thus the final of the extended source. Minus 1 by 4 log 2 1 by 4 here, plus 4 times minus 16 log 2 1 by 16 plus 4 times minus 1 by 8 log 2 1 by 8, that is 3. Since we have x0 2 3 3 bits is satisfied. Yes, we have verified. It is important to note that in DMS symbols are generally in statistically independent fashion, but most practical sources produce symbols that are statically independent or statically depends lower amount of information. The average information contains per symbol. Messages that are highly structured usually convey less information per symbol, hence the decrease in its entropy. A prime example of a source producing non-independent symbols in the English language, which, like any natural language, has a statistical statistical structure. As a letter is a multi-letter word, may depend on a number of preceding letters. Such a source producing different dependent symbols of 27 symbols with and a space. It's considered ergodic for it observed over a long time with everyone producing classification of source codes. Finally, some useful information after this English language example. So classification of source code, guys. The different types of source code. So here can you see the first one is block codes. A block code is a code that maps each of the symbols of the source onto a fixed sequence of bits. These fixed sequence of bits are called code words. The code word defining a block code may or may not have equal number of bits. Okay. So as the name suggests, block codes, a code for mapping symbols of source onto a fixed sequence of bits. Code words. Fixed length codes. Second, fixed length codes. Here, the length of the code word can be or cannot be have equal number of bits. But here, I think it is because it says fixed length. The simplest method to encode each symbol of a discrete source into the block of bits, where each block consists of the same number of bits. Yes, there are thus 2 to the power of m different blocks for a block of m bits. Assuming the number of symbols in the source is k, k is less or equal to 2 to the power of n, then a different binary m tuple may be assigned to each symbol. Okay. So whenever you have problem, just copy this. Uh, let's give it to Gemini. Let me just turn on the screen for Gemini. Okay. Explain in simple manner. Okay, let's see. Every symbol gets a code. Each of the symbol individually will represent a unique number of pattern of bits. All codes have the same length. This is called fixed length. Okay. How many bits do you need? You need enough bit of length m to give unique onto each of your key symbols. One bit and which one you can make 2 to the power 1, two patterns, 0 and 1. Not enough for 4 symbols. 4 symbols. To the power 4. Perfect. You can assign one unique. More than enough for 4 symbols. Okay, okay. So for k to the 4, to k is equals to 4, you need at least m2 is equals to 2. The formula mentioned is log 2k just tells you the minimum number of bits. For k is equals to 4, log 2 4 is equals to 2. The ceiling, visible ceiling is 2. So you need 2 bits. If you had k is equal to 7, k to 7 equals to 2.8. The ceiling is 2.8. There is 3. You need 3 bits because 2 to the power 4 is 4 patterns is not enough. And to the power 3, 8 patterns is. Okay, got it. See, Gemini explains in a much easier way than this so-called explanation. Variable length codes. Good. Variable length codes. The variable length code is one whose code word length is not same. Then what is the difference between block and variable? Let's see. The genesis of variable is based on the institution that efficient data compression can be achieved by mapping more probable symbols into shorter bit sequences, less likely symbols into longer sequence. Morse code of old telegraphy is the first application of the variable For example, E is represented by a single dot, but Q is represented by dash dash dot dash. Successive code words for variable length code are assumed to be transmitted. Okay, okay. With no demarcation of codeband boundaries, the decoder given an original starting point. Okay, okay. Distinct code. The fourth one. Distinct code, guys. Distinct code. Distinct means different. A code is distinct, also known as non-singular. Acha, it has another name, non-singular. If each code word is distinguishable from other code words, it is, however, possible that all the code words be distinct. Yet the decoding turns to be ambiguous. We therefore need to define an even more restrictive condition than non-singularity if we are to obtain practical codes. Okay. The fifth type of code is prefix free. Prefix free. Prefix is before starting and free. Instantaneous. Code. Prefix means starting, the starting part before the starting, and then it's free. So it does not exist. Any sequence consisting of the initial part of the code word is called a prefix of the code word. Okay. In a prefix code, no code word is a prefix of another code word. The decoding is of a prefix code can be accomplished as soon as the code for representing a source symbol is fully received. Prefix free codes are also called indigenous codes. No prefix. No code word is prefix of other CW code word. Uniquely decodable codes. Uniquely decodable codes. A distinct code must be uniquely decodable in that for each sequence of source symbols with a corresponding code word that is different from a code word corresponding to any other sequence source symbol. Decoding क्या क्या बातें कह रहा है एक ही वर्ड डिस्टिंग डिकोडेबल ये चीज रिपीट रिपीट Hmm. Interesting. Interesting. So codes, block, non-block, non-singular, singular, uniquely, non-uniquely, instantaneous, non-instantaneous. Let's study the craft inequality. Inequality. Consider a discrete memoryless source and assume the binary code word assigned to the symbol mi with probability pi has the length li bits and the number of the source is k. A necessary and sufficient condition for the existence of prefix free binary code is as follows. The summation of 2 to the power of minus length should be less than 1 and from 1 to k. Okay, which is known as craft inequality. Note that the satisfying inequality does not mean the code is automatically uniquely decodable. The inequality is merely a condition on the code word length of the code and not okay. The inequality does not show. Let's say, okay, here's an example. Okay, we'll solve this. Let's just have a small break of 5 minutes. So here I am with the example number 9.5. There are three codes for x1, x2, x3, and x4. 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. 0, 1, 1, 0, 1, 1, 0, 1, 1. 0, 1, 0, 1, 1, 0, 1, 1. Determine whether or not each of these three codes satisfy craft inequality. And if a code does, determine whether or not it's instantaneous. We first calculate the left-hand side of 9.8 for each code, then compare it to the one to determine otherwise. So here is this 2 to the power of minus L. So this is 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it will be summation C. To the power of 1, to the power of 3, to the power of 3, to the power of 3. And minus 3 will become 1 upon 8. So it will be in fraction. So it will be 1 upon 2 plus 1 by 8 three times. So here it will be 8, 6, 4 plus 3, 7 by 8. In the next code 2, 1, 3, 3, 2. So to the power of minus 1, to the power of minus 3, to the minus 7, minus 1. So it will become 8, 4 plus 2 plus 2. So 4 plus 4, 8. 8 upon 8, 1. The code word lengths of this code are thus acceptable. How? It should be less than or equal to 1. This is less than, yes. It is equals to. So it will be accepted of an instantaneous code. From the inspection of code by themselves, we can see the code is actually instantaneous and thus uniquely decodable. This is also acceptable. The inspection of the code themselves reveal that the for the code is prefix of another. How it is a prefix of another? Let's see. See, 110, it's not a prefix of this or this, but here 11 is the prefix of 110, so it is not instantaneous. It is instantaneous. Thus the code is not instantaneous. There, yeah, वही तो मैं कह रहा था. That is what I was saying about. In the third case, 1, 2, 3, 1, 2, 3, 2. So half 4, 1 by 8, 4. It will be equal to the denominator 8. 4 plus 2, 6. Plus 1, 7 plus 2, 9 by 8. It is greater than 1. So it is not a acceptable code word length. Yes, yes, yes. No, no, no. Extension codes. To achieve a more efficient code, extension code can be employed where rather than encoding integral accessible blocks. Ah, what happened is, you remember this was the extension code, k to the power of n. Yeah, yep. X to the power of n is n times hx. So k to the power of n is n times 1 upon n times in ln. Let's do the question directly. We'll understand. All six are block codes. Yeah, using 0 and 0 and 0. Oh, with the code word, yes. But none of them are extension codes. Okay. Codes where two are fixed length. Yeah, length 2. Here it's not fixed, not fixed, not fixed. Except code 1, all other are distinct codes. Yeah, because here 00 and 00 are same. All other are distinct codes. Yes. 2, 4, and 6 are prefix. 2, how? Only codes 2, 4 prefix free. Yes. Here the prefix of this is the prefix of this. And 2, no prefix. Here the 0 is the prefix of this. And 1 is the prefix of this. Here, no prefix. So this is prefix free. 0 is the prefix of all three. 1 is the prefix of none. So this is also free. Free, free, and free. Mm, Now here is the big point. Theorem, very important. Source coding theorem. Source coding. As soon as figure 9.4, let's see, we will not see, is a process by which output of a DMS is converted into sequence. Uh, Process by which output of DMS considered converted into sequence of bits. Okay. While meeting the requirement of being unique and uniquely decodable. Yeah, this was the average code length. PILI is the average code length. Average code length. Okay. Let L minimum denote the minimum possible value of average code length. We then define the code efficiency is L minimum length upon length less than one. Less than one. Okay, okay, okay. Wait a minute, wait a minute. Why does it yap so much? Source coding was a process to convert DMS into sequence of bits. Yeah, while being uniquely decodable. The objective is to minimize the average number of bits by reducing the redundancy. Why? Assuming that, yes, we all assume, then the minimum upon the actual length is efficiency should be less than 1. If it is 1, then the uh, how to determine Shannon's source coding theorem can provide the answer to this question. This theorem may be stated as ah, where is the theorem? First, it shows a block diagram. DMS, binary source coder, encoder. Sorry, my mistake. And bit sequence. Now it come into bit sequence. And here DMS was source symbols. Sorry, my mistake. Where is the theorem? This is theorem. The average coded length L of any distortionless source coding is bounded. Oh, what is this? Hx entropy should be less than length magnitude. Accordingly, the entropy Hx of a DMS provide a fundamental limit to the average number of bits. अच्छा जी, bits per symbol. Furthermore, L can be made as close to Hx as desired for suitably chosen row code. This theorem only gives the necessary and sufficient condition for existence of source code. However, it fails to provide an algorithm for the design of source code that can realize the performance predicted by this theorem. Note that minimum length equals to entropy. We may write the code of the efficiency as Hx upon L should be less than equal to 1. The source entropy provides a limit at which the source output can be compressed. Given a DMS of entropy Hx, the average length of a frequency will be bounded as uh, Hx plus 1. Furthermore, hmm, why does it have to say Hx? Why can't it just say entropy there or E? Why Hx? Haunting me. Let's solve this question. It's easier to solve numericals in this. Quite ironical. A source emits five equally like symbols. ठीक है. We have the probability. All of them have the same probability of 0.2. Find the interval hx. Find fixed length chords. When n is 1, 2, 3, determine the average number. Huh. Determine the average number of bits in each case. Comment. First we will solve the question, then we will comment. Is this a YouTube channel video or what? We have to comment. Okay, the hx according to hx formula minus log 2 1 upon pi. So here 1 upon 0.2 minus log 5 times. So just multiply 5. Oh, the pi will come as a multiplication factor also. Minus 5 times 0.2 log 2 1 upon 0.2 log 1 upon 0.2 is minus 1. No, that is the log of 0.5. Minus 2.3. Minus 2.3 is the answer. So multiplying with the minus 1, so minus 5, it will become altogether 2.23 bits. 2.32 bits. For n, very few code words, 5 code words, okay. With n equals to 2, 5 to the power of 225 code words. And n to the power of 3, 125 code words. Where this 3 came from? L was just P into L. Length. लेकिन अब सो गए, आपका एग्जाम है। Statement कर देना। Lossless data compression. Hmm. For efficient signal transmission, the redundancy should be removed. Otherwise, primary communication resources such as power and bandwidth are partially wasted. The process of to remove redundancy is called compression. Statement कर दीजिए। Statement कर दीजिए। And is transparent to end users. Removal of redundancy from the data with the condition that the original data can be recovered from the encoding binary system is known as lossless data compression. There are two distinct mechanisms. A compression mechanism that requires advanced knowledge of the message statistics. This leads to the class of entropy probability-based source coding, such as Huffman coding. So we have Huffman coding, entropy or probability-based. Huffman coding algorithm. Fixed length blocks of the source symbols are mapped onto the variable length binary blocks. Huffman is a prefix code which can be decoded instantly and uniquely. Huffman codes are formulated to be optimal code, that is, they achieve shortest average code length. The average length of the Huffman code is same as entropy if the probability of every code is not reduced by the source is an integer power of half. कुछ समझ नहीं आ रहा. Let's just do the question. Example number 9.8. The alphabet set of DMS consists of ABCDE 0.7, 0.1, 0.1, 0.05, 0.05. Okay. Shows two different Huffman trees and tabulates for each Huffman tree the code words. This means the two Huffman codes are as follows. L code 1 is 0.7 plus 1 into 0.1 plus 2 into 0.1 plus 3 into 0.5 plus 1, 0.1 into 2, 0.1 into 3, 0.05 into 4, and that is 2. So 1.6 bits. And here it is. Code 1. 1 0 0 0 1 1 0 1 0 1 0 1 0 0. So this was Huffman coding. Did you guys understood anything? Very fundamental views and